All right, video 2 is going to go through 2 examples of sampling distributions with independent random samples. Example 1 is going to focus on the difference of 2 proportions. So here we're going to talk about the sampling distribution of 2 proportions and talking about the difference between those. So example 1 is going to be, according to Mars Incorporated, 20% of plain M&Ms are orange and 23% of peanut M&Ms are orange. So suppose that you take a simple random sample of 240 of each candy. We're going to let p hat 1 be the sample proportion of orange plain M&Ms and p hat 2 being the sample proportion of orange peanut M&Ms. So we're going to describe the sampling distribution of p hat 1 minus p hat 2. So we're going to talk about the difference between these. In order to describe any sampling distribution ever, regardless if it's 1 sampler or 2, remember that we are going to need to use SOCs to do so. So we're going to describe the sampling distribution based off its shape, its center, and its spread. So first, talking about its shape, we're going to use the familiar rule that we talked about both in Chapter 8 and in Chapter 9. In order to figure out the shape of a sampling distribution, we must see if it's going to be approximately normal or not. And in order to do that, we test to see if N1P1 is greater than or equal to 10, N1Q1 being greater than or equal to 10, and N2P2, N2Q2 respectively also being greater than or equal to 10. So we just need to use substitution now. So our sample size here for N1 is going to be 240, and our P1, we're going to allow that to be 0.2. So simply taking the product of those will give me the answer here. Remember that Q1 is just going to simply be 1 minus 0.2, which should give you 0.8, and then we're going to substitute that in there. Similarly for N2, that's going to be 240. Where P2 is going to be 0.23. So taking the product of those and putting that into the third one. Q2 is going to be equal to 1 minus 0.23, which should be a 0.77, and we're going to replace it there. So using substitution, it should look something like 240 times 0.2, 240 times 0.8, 240 times 0.23, and 240 times 0.77. And we need to test to see if all these are going to be higher than or equal to 10. And doing that simple math, we get 48, 192, 55.2, and 184.8. And all of those values are greater than or equal to 10. Now, since that condition is met, we're now able to make the statement that the sampling distribution of p hat 1 minus p hat 2 is approximately normal. So the only change here is that you actually have to do NP 2 more times for that second sample. And then when we make the comment here of the sampling distribution, we must remember to do p hat 1 minus p hat 2. And we're basically doing the same thing that we've already done, just with an extra sample, just a little bit more work on there. Talking about the center, we need to remember that we're going to use the mean of p hat 1 minus p hat 2. So I forgot the 1 there. But remember, that's simply from your notes from the last video, p1 minus p2. And again, that's just simply subtracting the 2 proportions, 0.20 and 0.23. So when I do that, that gives me a simple answer of negative 0.03. So this means that on average, there's going to be 3% more orange peanut M&Ms in a bag compared to orange plain M&Ms in a bag. So we expect a higher percentage, 3% of the time, a 3% higher percentage for orange peanut M&Ms in comparison to orange plain M&Ms. So that's what that one's saying. For spread, we have the formula that we discussed. That should be the square root of P1 P2 over, or P1 Q1 over N1 and P2 Q2 over N2. You can see I've already substituted in the values there, and we need to kind of compute that. So you need to carefully compute that in your calculator. So take a minute and make sure that you do that. Once you do get that, that should give you an answer of 0.037. So 0.037 should give you the standard deviation of the difference between p hat 1 and p hat 2. And then you need to wrap it up in a sentence there. So wrap it all together in a sentence. So we're going to state that the sampling distribution of the difference of the proportions of Orange plain M&Ms and orange peanut M&Ms is approximately normal with a mean of negative 0.03 and standard deviation of 0.037. So only thing we need to do in order to describe the sampling distribution of p hat 1 minus p hat 2 is to discuss the SOCs, and we did that earlier going through the shape check, the center check, and the spread check. All right. Once you guys get that, we're going to go to second one where it's going to ask us how to calculate a probability. So what is the probability that you select a higher proportion of orange plain M&Ms than orange peanut M&Ms? So remember that we are trying to figure the probability here that the difference here is going to be greater than 0, because if we have a higher proportion of orange plain M&Ms, that means that p hat 1 will be greater than p hat 2. So p hat 1 will be greater than p hat 2 because we're talking about plain being bigger than or greater than peanut. All right. Now earlier on the slide previous, we were talking about the difference between p hat 1 and p hat 2. So we were simply subtracting there. Here we can do that if we subtract that peanut to the opposite side or of that inequality. And when we do that, that's going to give us that p hat 1 minus that p hat 2, because p hat 2 is represented by peanut. So we're basically trying to say, is the difference greater than 0? So what's the probability that that difference is going to be greater than 0? And this is when we're going to use our familiar z-score. So here the observation that we're interested in looking at should be the difference being 0. All right, so the observation is the difference being 0. All right, with a mean of negative 0.03. So notice here that we do have a minus negative 0.03. And that's because we found that on the previous page. So don't get confused where that came from. Remember that this is the mean of p hat 1 minus p hat 2. And this is the standard deviation of p hat 1 minus p hat 2. So we just need to use those and use a z-score. And remember, since we said that the distribution was approximately normal, we're able to use normal CDF. So go ahead and type that in and see if you can find the probability for that. After you type that in, you should be able to get the probability of 0.2089. So what we're able to say here is that there's basically a 20.89% chance that we will select a higher proportion of orange plain M&Ms than orange peanut M&Ms. All right, so there's about a 20% chance of that happening. So remember, it's more likely for us to get a higher proportion of orange peanut M&Ms because we expect about 3% more on average. Okay, in a randomly selected bag there, due to that mean. Going to the means of a sampling distribution. So we're now going to talk about sampling distributions with independent random samples for means. We're going to do the same thing. So it's going to be very similar, but this time, instead of talking about P's and P hats and Q hats and Q's, we're going to be talking about X bars. So you need to shift your thinking from proportions to means. So our example here is going to be the weight of pugs, which is a type of dog, are normally distributed with means of 16 pounds and a standard deviation of 0.7 pound. The weights of Pekingese dogs are also normally distributed with a mean of 14 pounds and a standard deviation of 0.5 pound. Suppose samples of size 15 are selected from each breed of dog. We're going to let X bar 1 be sample mean weight of pugs and X bar 2 be the sample mean weights of Pekingese dogs. So now we're going to describe the sampling distribution of X bar 1 minus X bar 2. All right, so before you guys start using the central limit theorem, remember that in the problem there it said that the weights of these dogs here are going to be normally distributed. I'm unable to write all of a sudden. Oops. Okay, I just need to edit that out. All right, so to describe the sampling distribution of x bar 1 minus x bar 2, we're going to use SOX again, but make sure you remember that the weights here are normally distributed for pugs, and they're normally distributed for Pekingese. So here, we don't have to do anything with the central limit theorem. The only thing we need to state here is that given that the population distribution of pugs and Pekingese are normally distributed, we're going to assume that the sampling distribution of their differences is also normally distributed. If you take something that's normal and you subtract something that's normal, you're going to get something that's normal, and that should make a lot of intuitive sense there. If you have something that's normal and you subtract something that's normal, you're going to get something that's normal. So this statement right here is allowing us to say that. So again, given that the population distribution of pugs and Pekingese are normally distributed, we can assume the sampling distribution of x bar 1 minus x bar 2 is also approximately normal, okay? So since the populations are normally distributed, so are the sampling distributions, all right? Talking about the center next, we're going to continue to use SOX to describe the sampling distribution, regardless if it's going to be the difference of proportions or, like this example, the difference of means. From the previous notes slide, remember that mean of x bar 1 minus x bar 2, as like you see it on the slide there, just mu1 subtract mu2. So that's simply going to be 16 minus 14, which is going to give you a positive 2. So here we're talking about the average weight of pugs seem to be 2 pounds more than that of Pekingese. So the average weight for pugs is 2 pounds heavier than that of Pekingese dogs. Talking about the spread, the only thing you're going to do there is discuss how to find that, which is simply going to be plugging it into the formula that we derived in the previous video. So for x bar 1 minus x bar 2, and we're trying to find sigma of that, that's going to be the square root of the standard deviation squared over its sample size, which is going to be 0.7 squared over 15, plus the standard deviation of the second one, which is going to be for Pekingese, which is 0.5 squared, and dividing that by 15. So take a minute, grab that calculator, type it in, and see what you guys get. If you guys get it, it should be 0.22, so you have a standard deviation weight of 0.22. Wrapping it together in a sentence, we're going to say that the sampling distribution of the difference in the mean weights of pug and Pekingese dogs is approximately normal, with a mean of 2 pounds and a standard deviation of 0.22 pounds. All right, so just simply making a statement after finding both the mean and the standard deviation, and that's it. On the next one, we're going to say what is the probability that the difference in mean weights of samples of 15 pugs and 15 Pekingese is within 1/2 pound of the mean. So that means it's going to be within 1/2 pound of the mean. Well, the mean of x bar 1 minus x bar 2 was going to be 2 pounds. So if you're within 1/2 pound of that mean, that means you're going to go 1/2 pound below 2 and 1/2 pound above 2. So that means we're going to figure out if it's between 1.5 and 2.5 pounds. So we're going to find the probability that the x bar 1 minus x bar 2 falls between 1.5 and 2.5. All right. So again, we're going to use our z-scores. Okay, observations being the 1.5, so this would be observation 1, and 2.5 is observation 2. Plugging that in your z-score formula, you're going to do 1.5 minus 2 over 0.22, and 2.5 minus 2 over 0.22. If you don't like that, remember you can just normal CDF it with 1.5 and 2.5 as both the lower bound, so this is the lower one, whereas 2.5 is the upper bound. Mean is still going to be 2 with a standard deviation of 0.22. And if you calculate that probability, go ahead and take your calculators to calculate that probability really quickly. The probability of doing that is going to be 0.977, so it is very likely that that's going to occur. So there's a 97.7% chance that the difference in the mean weights of 15 pugs and 15 Pekingese is within 1/2 pound of the mean. So it's very clustered around the mean, and that makes a lot of sense because our distribution is approximately normal. All right, so we have that normal distribution there, and it makes sense that a lot of the data is clumped within 1/2 pound of the average. What difference in mean weights of samples of 15 pugs and 15 Pekingese is at the 40th percentile? Remember, with percentiles, this means that we have observations below that value. So if you've been to AP review, we've reviewed this recently. This means that observations below the 40th percentile. So what is that going to be in terms of the mean weight? So remember that we use this difference here. We use inverse norm to figure out that observation. So that observation there should be 0.4 for the area for inverse norm, 2 and 0.22. So if you plug this in, this is going to give you that weight there. So that's going to give you that mean difference weight. So we're going to need to figure that out. All right, so what is the mean weight? What difference in mean weights of the samples of 15 pugs and 15 Pekingese is at the 40th percentile? All right, so we're trying to figure out what the probability that x bar 1 minus x bar 2 is going to be less than in order to get 0.4. All right, so we're interested in getting the 0.4 probability. When we want to go backwards, remember that we use inverse norm to do so. So inverse norm will give us that observation that we're looking for. So what difference in mean weights will be at the 40th percentile? So we're interested in finding that observation. Remember, if we do inverse norm, we're going to plug in the area, the mean, and the standard deviation there of the difference there. So remember that we're going to type in 0.4 for the area, mean sub d, which is the mean difference there, and then the sigma sub d is going to be the difference between the weights. So go ahead and take a minute and see if you can figure out what difference in mean weights would be at the 40th percentile. And that mean difference is going to be 1.94. So a difference of positive 1.94 pounds represents a difference in the weights of pug and Pekingese dogs at the 40th percentile. All right, so simply typing this into inverse norm will help you figure out that difference, okay? Doing another one here, but this time, what difference in mean weights of the samples of 15 pugs and 15 Pekingese is in the top 5%? You guys should remember that if you're in the top 5, you're also in a percentile. That percentile should be the 95th. So top 5% means that 95% lie below it. So here we're going to do the same thing we did on the previous slide, but we're going to use inverse norm for 0.95. Okay, so inverse norm for 0.95 would be the top 5%. So take a minute, type this in your calculator and see what you get in terms of the difference in the mean weights for these samples. Sample mean weight should be, the difference is 2.36. So that means a difference of positive 2.36 pounds or more represents the weight, a difference in the weights of pugs and Pekingese within the top 5%. So the last two questions, 3 and 4 for your examples, really highlight and go over like using inverse norm and going backwards instead of trying to compute a probability. All right, this concludes video 2. So please make sure you're well versed in both video 1 and video 2 before coming to class tomorrow. You need to make sure that you're able to hit the ground running. We're going to work on some example problems, address any misconceptions, and then we're going to keep moving forward. All right, see you later.